Good morning. Oh, come on. We can do better than that. Come on, let's try this again. Good morning. Very good. I mean, there's caffeine, there's food. We're at this amazing conference. We've had all these amazing talks leading up to here, and you got a guy with a big beard up here. Come on. So, this is not my first time on this stage. Very excited to be back at Web Summit, to be back in Ireland. I lived here for a number of years and absolutely love this place. So I'm glad you guys are getting to experience a small portion of this. So, machine learning. The rise of the machines. I am here to accept my machine overlords. I think that this is inevitable. It's coming, as Angus and some of the other people this morning have talked about. But I want to break it down and talk about what is machine learning. What does that actually mean? And give you some practical examples and some practical thoughts on this. So, first of all, machines, they're logic machines. They do math. One of my first ever tech mentors told me that if I tell a machine to step forward, take a right, and walk into the wall, it's going to do it. And if I tell it to start over and take a step forward and take a right and walk into the wall, it's going to do it again. And it's going to do it again and again and again and again until I program it to do something else. Okay, so machines are doing what we tell them to do. Now, with this artificial intelligence and machine learning, they're starting to figure out what they're doing on their own. But the reality is, it's all based in data, all based in what we tell them and what information we give them. So I'll give you the simplest example of machine learning. You're my machines, okay? So if I tell you A equals 2 and B equals 4, C equals 6. Very good. Some cheeky bastard said 5. I'm going to find you. So, but that's all the machines are doing. They're just doing it on a much, much larger scale. And by much larger scale, I have a customer who has 43 petabytes worth of data. 43 petabytes. Let me get your head around this number. When Bing or Google or any of the other crawlers take a snapshot of the entirety of the internet, the compendium of human knowledge, that is 13 petabytes. And this customer has almost 3 times that. That's amazing amount of data. And they're able to feed this into algorithms so that you can, with very, very crystal clear precision, be able to say, oh, this is the outcome because we have all this history that we're able to train on and look at and say, based on all of this, this is probable, okay? But, I mean, it's the same thing as we do. If you're looking at a shirt, you look at this shirt and you know what this shirt is roughly made of because you've seen thousands of these. Well, what if I fed a computer 1 million images of cotton up close? How accurately could it look at cotton and say, yes, that's cotton? Okay, it's the same thing that we do with our brains. That's what we're training these computers to do. So we have this in our everyday life. So right now, you're already seeing the results of this snuck in beautiful ways inside of your own systems that you're using every day, such as your spam filters. Those keep getting better and better and better and better. There was a time 5 or 10 years ago where spam was the bane of my life, and I was getting literally hundreds or thousands of messages a day. How many people are seeing spam in their inbox on a daily basis these days? Actually seeing it, not receiving it, seeing it. Handful of hands. Well, there are better spam protectors out there, just saying. So, because you look at everybody else in the room and nobody else is actually seeing this spam. You get it, but it's very smartly filtered off. But the beautiful part is how many of the important emails that are actually real emails are getting caught in those same spam filters. It used to be a lot, and it has dribbled down to very occasionally I'll end up with something in my junk mail that was meant for me actually as a person. So this is getting built into our life. How many people shop on, online? How many people shop on Amazon? If you didn't raise your hand, you're probably in the wrong room. I'm just saying, okay? How many people get recommendations of, oh, you looked at this, you might be interested in this? Again, how many people like that? It's about half and half, right? So that is an example of we're seeing the results of machine learning in our daily life, and we're starting to, even when I go to Netflix, or when I go to Amazon, or when I go to, name your site on the internet that my wife also happens to go to, we have very different pages. Mine's like sci-fi and killer robots and drones, and hers is not that. I mean, just saying. So, but we're seeing this creep into a lot of interesting places, like predictive analytics. Predictive analytics is a cool one. We have a elevator company that we've been working with, Tyson Group, and they figured out a very simple problem that they had, and they asked our help to go fix this problem. The problem was, it cost them $600 to send a guy to the elevator. Okay, it doesn't matter what he does at the elevator, it costs them $600. If he replaces the motor, if he replaces a light bulb, it's $600 to get him from the office to the elevator. So they started looking at that and they went, well, what could we do that would improve upon this model? And so we have to send people out less. And so we started looking at that and went, okay, with predictive analytics, we can look at the lifetime of these various components inside of an elevator. And so if we're gonna send somebody out to go replace a pulley, we might as well send extra light bulbs with them, not just every time they go out, but when we have looked at it and said, yes, with the lifetime of this elevator, with the service that this elevator has been in, with the location that this elevator has been in, with the power fluctuations that part of the town have been under, with all of that data, we're likely to have a light bulb go out in the next 3 months, 6 months. So we might as well go ahead and send extra light bulbs with the repairman and have him go ahead and replace those. Because it's gonna be $600 whether he replaces the light bulbs or not. He's already going there to replace the pulley. That make sense? Seeing a few nods, a few glazed over looks. We're all good. Okay, so we're actually using this very heavily in things like price predictors and other things. So if you're buying flights, say to come here to the Web Summit, you would notice that a year ago the flights were very cheap. As you got closer, the prices started to get a little more expensive because the flights started to sell out. Well, we're able to look at what happened in this area last year and the year before, and see that there was a rise in prices. So the fun part is, this is a social experiment I'm going to play, is I'm going to look at flights for early November next year when this is in Lisbon and see what happens and see if the prices are predicted to go up or not. So we talked about the predictive maintenance and that kind of stuff. Predictive assistance. So everybody in the room has probably used a predictive assistant of some sort. And by these, I'm talking about Cortana, Siri, those types. How many people have used those? All right. Again, if you've not raised your hand, you're probably in the wrong room. The predictive assistants, these are getting amazingly capable. As in, I'm able to, pull up and tell Cortana, next time I go by a grocery store, remind me to buy eggs. Okay, that's an indeterminate, I have no idea when I'm gonna go by a grocery store next. I know that I will at some point in time, and when I do, when I get close enough, Cortana will pop up and remind me, oh, Josh, you needed to buy eggs, you should pop in. Like, okay, great. Well, think about all that went into that. As a human, we're able to crunch a lot of that data very quickly in our own head, but we're a fuzzy logic machine. When you start thinking about what goes on in a computer, you've got the array of all the grocery stores, you've got time factors, you've got GPS factors, you've got what the note was and what it was that we needed to go pick up, and you start putting all those things together and it becomes a very interesting set of problems. So we're seeing that come into our everyday life. But the basic workflow is the data science workflow and our experiences there. So machine learning, I'm just gonna go ahead here. So when it comes down to machine learning, the basic way that this works is that we pull out a set of features. Okay, now if you're a relational database guy, it could be a table with columns. So you think about the columns, but it's some data that we can assign a name to and say, okay, that is that's the first name, that's the address, that's the, whatever it happens to be. So we pull out the feature set, and the feature set is, again, what our data is. Then we're going to apply a learning algorithm. And there's a number of different types of learning algorithms, and I'll talk about some of those in just a minute. And then that's going to pull together a trained model. So let's go back to my example earlier of A equals 2, B equals 4, C equals 6. Hey, we're very good. All right, we remember, we're still trained. And then what we do is we expose that as a service so that we can ask it future questions. So if I say D, you will say 8. Very good. See, this is a beautiful algorithm. It works well. So what you don't realize is that what you're doing is you're a linear regression algorithm. Okay, so we have here the basic workflow, and so the features describe the domain, so income, age, et cetera. Labels augment the learning data, okay? So for example, this photo contains a man or a cat or a, whatever it happens to be. This cloth, cotton, silk. Depends on how deep you want to go, okay? Or in the example of natural language processing, you start looking at tweets. One of the things that my team is working on is doing emotion analysis of tweets. Is somebody angry, upset, happy, and getting down finer and finer and finer? Well, what we need for that is we need some number of tweets that are labeled. So we're going to go through and say, okay, we read this as a human and say this one is angry or upset or happy or overjoyed, whatever it happens to be. And then we will run that through to train the model. Once the model is trained, then the computer can start attaching those labels in the future. So unsupervised learning, there's unsupervised and then there's supervised. So unsupervised, if you think about all the stuff that was in the last session, for those of you who were in the last session, LinkedIn, he was looking at the social graphs. And my favorite one is he pulls up and he says, in my network, let's take a look at my network. And all we're doing is we're trying to find insights that we didn't necessarily know were there. And so we're going to look at my social network, and it pulls out and says, oh, there's these 30 people that have something in common, and that is, these 30 people are all from the same university. Huh, okay. These 45 people are all from the same company. Okay, all right, interesting. These people are all connected in some way. They're, in some medieval reenactment society. And it starts pulling these things together, and I go, interesting. That's where my professional network lies, is lots of people who do acting in medieval reenactment societies. Great. Is that where I want it to be? But it's a new insight that I didn't realize was there, and that's what unsupervised training starts to do. Supervised training uses labels so we know what it is. So for example, if I start looking at housing data, and I want to look at the housing data and I want to say, cost per square foot, and start looking like here in Dublin, and I'm able to pull up and say a house that is X number of meters, let's say that it's going to be 90 meters downstairs. How much is that going to cost? And we start applying numbers to that, and then we can say, okay, based on that, if I take a 100 meters or 200 meter house, what does that mean? And likelihood is it's going to be priced at this level. Okay. Again, that's linear regression. We start. That is supervised training, meaning that we know what we want to predict, and in the future we're going to be passing values and getting back a probability of is it this or that or the other thing. Now that one's a very simple one in that we've got price per square meter, price per square foot, whatever it is. We can have much more complicated things. So in the case of ThyssenKrupp, they're looking at 7 or 8 different variables, and all of those things added together equal the probability that this thing is going to happen or not happen. But again, we're looking for supervised data. We know the question, we know the type of answer that we want. We're not just looking for additional insights.
The additional insights bit is, let's say we take that same housing data and we start looking for, well, let's say we don't know that square footage is the pricing indicator. Well, in fact, we may not know. So what is the pricing indicator? And we start running large amounts of housing sales over the past number of years. So was it proximity to Dublin Center? Was it proximity to the local light rail? Was it the, what is it? What is it that actually affects price? And that will start clustering things in interesting ways. And we can start learning what are the variables, what are the things that actually start to matter. So, so this is basically the way that it works, is we go through and we train the model. We take our data set, whatever that data is, and I'm cheating here a little bit because once you get to here, this is actually not necessarily the hard part. The hard part is getting the right data set, getting clean data that is well-groomed and ready for the work here. So a true data scientist is going to giggle at this particular slide because I'm showing the easy bit. It's like looking at an Olympic runner and going, they ran 100 yards and we're praising them. No, it's not the 100 yards. It's the 5 million yards that they ran in the past 5 years that have led to that 100 yards. That's kind of what we're talking about here. So this is the last 100 yards. Take our data set. Step one is we take, for easy math's sake, we're going to say we have 100 rows. 100 rows. And what we're going to do is we're going to split that data, and we'll split it into 50-50, 70-30, 80-20, whatever split makes sense. And we will take the first side of that, and we'll go train the model. And what that means is we will look at it and say, okay, we're going to give it A equals 2, C equals 4, D equals 8, and then we'll run that through our training data, and that will train the model, and now our algorithm is ready. And then we will test to see if we're right by saying, okay, we know B equals 4, right? It's a known quantity. So we're going to ask our model, what do you think B is? And if it comes back with 4, we go, hey, we were right. Okay, model is ready to go. We can release this into the brave new world, and we go make our $1 million, right? Woo! So that's basically how it works. So that's the test data and scoring the model, is seeing how accurately we predicted that particular model. Now, you wouldn't do it with 4 cases. You would do it with 10,000, and you would split it and say, I'm going to use 7,000 to do my training and 3,000 to do my testing, or something like that. And that would come up with a very accurate prediction of how accurate is the model. So, all right. Everybody with me so far? All right, very good. So different types of tasks require different types of algorithms. So to find similar companies, or to start looking at what are the things that affects pricing, or what unsupervised training. K-means clustering is one of the most predominant ones out there. To start doing predictive of hourly bike rental precision. So how many bikes are going to be rented downtown? The one you guys were talking about, the A, B, C, D. That's a regression tree, okay? And then we have things like credit risk, which is a decision tree. So those kind of the big 3. There's more than that, but those are kind of the big 3 that if you know what those are, you can get a good start and get a good running go at it. So actually, I think I've got a slide here in a second that shows. Yeah, I'll pop back to one in a minute. I thought I had a slide on that. Maybe I deleted that slide. So yes, I deleted that slide. Sorry about that. All right, we'll come back. I need to add that slide back in next time I do this talk, because it's a good slide. Sorry, it's an amazing slide. It would blow your mind. Explain the whole thing. So the regression tree, imagine a line, okay? And if you think about the A equals 2, B equals 4, that's a straight line this way, okay? Imagine it's a little more complicated, where A equals 2, B equals 2.6.
and then C equals 3.9. And there's these weird randomizations, but there's a curve of some sort. What the regression tree is going to do is it's going to try to stay very close to that. Okay, the decision tree is very similar. Okay, except that it's going to be coming with a probability factors of, if you think about, they defaulted on this loan, so that's a minus 0.9, but they paid this one, so that's a plus 0.3. Okay, so somewhere in between, we're mathematically mapping that line, and we're able to say with good probability this is yes or no, are they a good credit risk or not. Okay, the regression tree, the line already exists, and we're predicting are they going to be north or south or close to that line. Does that make sense? So it's a slightly different take on the same problem. And the k-means clustering is grouping things. Now, there's a lot of different tools that are out there that are ready to go. The two primary programming languages that people use are R and Python. Then there's a bunch of open source tools out there. Mahout's pretty good, Weka, and then there's a bunch of commercial tools out there. MATLAB is probably the most well-known, but SPSS and SAS have been around for a while. The new kid on the block, biased, I'm granted, I'm biased a little bit, granted I'm biased. Azure ML, I work for Microsoft. So the Azure ML is a new one on the block, and we're turning some heads with it. It's pretty cool, and encourage you to check it out sometime. That's the only pitch. So, but like I said earlier, when you get to I have a data set, starting to pick algorithms, that kind of stuff, that's the last 100 yards. The real rest of it, the other 5 million yards, is what problem am I solving? That is the question that people, data scientists, real data scientists, spend their entire life trying to answer is, what is the actual question? And they will spend months deliberating on what is the actual question. And these are people that are much smarter than I am and have more patience than I am. I'm a little more ADD. So define the goal, then what information, what data do I need? Now, sometimes you're given a data set and you're told, go figure out what you can learn from this data set. But most of the time, you're able to start at the beginning and say, what is the question that I want to answer? Now, what data do I need to collect in order to answer this question? Then you start finding patterns in that data, and you start building out that model. And you figure out, okay, now that I've built the model, how do I critique that? And how do I evaluate that model? And so does the data that I have and the model that I have picked, do they actually answer the question with some reasonable amount of precision and accuracy? Then, if they do, you deploy the model, and then you learn from that over time. So let's take the airline price analytics. I'm able to look at that and go, historically, this is, the prices to Dublin at this time of year went up. And so next year, my prediction is that the airlines will, the price prediction engines will predict that the flights are going to go up, when the reality is they're not going to go up that much. And so next year, we're going to have to retrain the model to look at the actualities of what happened and how accurate were we, how many recalls did we have. Okay, so the big question is, the big point is you have to ask what the right question is. So when will the clutch fail? I don't know. Will the clutch fail? Yes, someday. I don't know when, but I know it will. What is the probability that it will fail in the next 3 months? That's a question I can answer with machine learning. I can't necessarily give you a day. I can give you a strong probability. I can give you a probability of some percentage, 90+%, that it's going to fail within the next 3 months. But I can't necessarily give it an exact date. But what is the probability that the clutch will fail within the next 3 months? That's a great machine learning question. And we can feed it a tremendous amount of information about driving patterns, weather, age of the car, age of the clutch, torque on the engine. There's a whole bunch of stuff that we can feed it that will give me a strong probability. But when, not a great question. Will, definitely not a great question, because the answer is yes, it will at some point in time. So some of this is a little bit repetitive. So quantize, yeah, actually, you know what, I'm gonna skip that one as well. So the question is, how good is your data? So if your data is extremely strong and extremely good, you actually don't need a tremendous amount of it. I mean, once you have seen X number of cotton shirts, at some point it doesn't really matter if you see another 5 or 10 or 100 or 150. What matters is, okay, I've seen enough that I understand what this looks like. The quality of the data is what starts to matter. So, you know, thinking about the ThyssenKrupp scenario, if I have no scenario under which the light bulb has ever failed, then I have no way of predicting when that light bulb will ever fail, okay? If I have a 50-50 of here's when it failed, here's when it didn't, now I can start looking at that. Was that bell for me? Yes? Okay, I'm over. All right, so then I can start looking at it and I can start fairly accurately predicting, yes, it's going to fail, no, it's not, because I know that I have started looking at that. So this is what I talked about earlier. This is what a more real world scenario looks like. Only imagine 9 of those or 12 of those going on. Lots of ways to validate the data. Great math. This is the slide I was looking for earlier. I stopped one slide too short. This is the slide, mind-blowing. I'll show it to you on the Microsoft stand if you want to take a look at it. So, in closing, hopefully this has given you a little bit of a primer in machine learning. Hopefully you understand a little bit more about it. And if you have any more questions, feel free to reach out to me at Josh Holmes, or you can find me at joshholmes.com, and then josh.holmes@microsoft.com. Thank you very much.